Hello, a great welcome to this series on engineering mechanics. Myself Jarajan P. This is class 3 of the series. It covers the following topics. 1. Components of a vector. 2. Representation of vectors. 3. Concepts on magnitude and direction cosines. And finally, the fourth topic, definition of unit vector. So let us start our class. In the last class, we discussed how to obtain the resultant of a set of forces. Today we will see how to obtain the components of a vector along any two directions. So we will start the class with this topic. So look into figures A and B. Here is shown a force F whose components are to be determined along two arbitrary directions represented by U direction and V direction. So how to obtain the components of force F along the U and V directions? So what is to be done here is very simple. We draw a line, two lines, each line being parallel to the U and V axis. Look here. So from the head of vector F, we have drawn a line parallel to the V axis, and we have also drawn a line parallel to the U axis. Now, in order to find the components vector Fu and vector Fv, what we do is that we simply join the tail of vector F to the intersection points of these lines on the U and the V axis. So this is how the components looks like. So as we can see here again, vector Fu and vector Fe are the adjacent sides of a parallelogram, and vector F is nothing but the diagonal of this parallelogram. So in order to find the components, what we did, we simply applied the reverse of the parallelogram. That means from the head of vector F, first we have drawn lines parallel to the U and V axis. Where these lines intersect the U and V axis, we have connected these intersection points with the tail of the vector F in order to obtain vector Fu and vector Fe. So in the vectorial notation, we can say that vector F is equal to vector Fu plus vector Fv. So please remember here that U and V are any two arbitrary directions. In many cases, we are interested in obtaining the components of a given force along U and V axis where the U and V axis are orthogonal, or in other words, the angle between the U and V axis is equal to 90 degrees. So in this case, as you can see, the U and V axis are shown. As you can see that the angle between the U and V axis, it is equal to 90 degrees, and we would like to find out the component of vector F along the U axis. So referring this sketch, obviously as discussed earlier, what we do is that from the head of vector F, we draw a line parallel to the V axis. We also draw a line parallel to the U axis. And finally, in this specific case, instead of a parallelogram, we obtain a special case. We obtain a rectangle. Accordingly, where the U and V axis are orthogonal to each other, we call the respective components as the so-called orthogonal or the rectangular components of the force vector F. So referring this sketch, if beta is the angle which the force vector F makes to the U axis, we obtain the magnitude of the component along the U axis, that is Fu is equal to the magnitude of the vector F, which is indicated by symbol letter F, into cos beta. Similarly, we obtain the magnitude of the component along the V axis, that is Fv, as F into sin beta. And here I have put up a small note. All throughout this discussion, whenever vectors are to be denoted or to be written, we use an arrow on the top. For example, look here. Vector F, I have put an arrow on the top, and the magnitude is denoted by a symbol letter, that is F. Okay, so the force vector is denoted with an arrow which is indicated on its top, and the corresponding magnitude of the vector force vector F is indicated by the symbol letter F. Okay, this is what is being indicated very specifically for the proper guidance of the students. Okay, so now how to represent the vectors? That's a very important thing, because a vector can be in 2 dimensions or it can also be in 3 dimensions. So what must be the proper coordinate system that we should use. So this is what we are going to discuss. So as written over here, let me just zoom it a little bit. Yes, to represent the vectors, we shall use a right-handed XY coordinate system. This is very important. And this XY Z coordinate system is established as per our right-hand system. So when do we say that a rectangular coordinate system is right-handed? So this is what is written here. A rectangular coordinate system is said to be right-handed if the thumb of the right hand points in the direction of the positive z-axis, when the right hand fingers are curled about this axis and directed from the positive x-axis towards the positive y-axis. So look here, this is what is being demonstrated here through this, the sign convention for a right hand Cartesian coordinate system. And in this case, you can see that this is your right hand. The thumb of the right hand, okay, it points in the positive z direction when the fingers are curled about this z-axis. That is very important, okay. So the thumb of the right hand, it points in the positive z direction when the fingers of the right hand are curled about the z-axis. And please remember that the curling, the sense of curling, it must be from the x-axis to the y-axis. Okay, so this is what is written very clearly here. When the right hand fingers are curled about the z-axis, okay, about the z-axis, and directed from positive x to positive y. So what you do is you simply curl the fingers of your right hand, okay, the direction or the sense of curl is from x to the y-axis, then the thumb of the right hand will point in the positive z direction. So such a system is what we call as the right-handed XYZ coordinate system. And remember, XY is in the horizontal plane and our Z is the vertical axis. So how to express or how to represent any vector in such a right-handed XYZ coordinate system? This is what we are going to discuss now. So look here, as discussed, this is the coordinate axis. So we can say that this is your x-axis, this is my y-axis, this is the z-axis, and O being the origin of the coordinate system. And I have a vector OA that is represented by the vector F. And I would like to find out the component of vector F along the x, y, and z axis. And here, as clearly indicated in the figure, vector fx represent the vectorial component of f in the x direction. Similarly, vector fy and vector fz are the components along the y and z directions. So how do we obtain the components vector fx, vector fy, and vector fz, so that vector f can be written as vector fx plus vector fy plus vector fz. So how do we obtain vector fx, vector fy, and vector fz? This can be done by applying the parallelogram law twice. So what we need to do is, first, the given vector f, so this is my given vector f, okay, that is represented by vector OA. It is first projected into the z-axis. So look here, that means from the head of the vector OA, you have to draw a line, okay, that is parallel to my xy plane, where it intersects my z-axis. It provides me the vectorial component in the z direction. So I have the vector fz. Okay. Now please remember that my xy plane and my z-axis, they are at 90 degrees to each other. Okay. So I obtain my vector fz. Now what is done is that similarly I project. Okay. I draw a line. Similarly I draw a line from the head of the vector OA, that is from the point A line parallel to the z-axis where it intersects the xy plane. That intersection point I have directly joined with the origin O. Thereby I obtain a component of vector f in the xy plane. So the first application of the parallelogram law, it includes obtaining the components of vector f in the z direction as well as in the xy plane. So we can say that from this diagram, vector f is equal to vector fz plus vector xy. So now vector fxy, which is the component in the xy plane, now we will resolve it along the x and y axis again using the same parallelogram law. So what we do is that, so this is my vector fxy. So as usual, from the head of vector fxy, I will draw two lines, one parallel to the x-axis and the other parallel to the y-axis. Where these lines meet the x and y-axis, that provides directly the component of vector fxy along the x direction, that is vector fx, as well as the component along the y-axis, that is my vector fy. So we can say that finally vector f is equal to vector fxy plus vector fz. But my vector fxy has got its rectangular components, that is vector fx and vector fy. Accordingly, finally we obtain the components of vector f as vector fx, vector fy and vector fz. Remember, these components are being arrived at by applying the parallelogram law twice. So in the vectorial format, we can say that the vector f is equal to vector fx plus vector fy plus vector fz. Remember, these are vector fx, this is a vectorial component, similarly vector fy and vector fz. Okay. Now let me introduce you the very important term, that is a Cartesian unit vector. So these Cartesian unit vectors are very much used in the representation of vectors in the Cartesian space. So here as written, the Cartesian unit vectors I, j and k are used to designate. So these symbols are used, I, j, k are used to designate the directions of x, y, z and axis, because you know that whenever we have an axis, it is important that we specify the directions of this axis very clearly. So we use the unit vectors I, j and k in order to designate the directions of x, y and z axis as shown in the figure. Look here, this is my x axis, this is the y axis and z axis. So let me just zoom it a little bit. Okay, so as you can see that here I have marked vector I. So vector I, it's a unit vector. What do you mean by a unit vector? It's a vector whose magnitude is equal to 1. And when I say vector I, it means that it is a unit vector whose direction is along the x-axis. Similarly, j is also another unit vector, but it is directed along the positive y-axis. So similarly, we have vector k, that is another unit vector but directed along the positive z-axis. Or in nutshell, I, j, k are the unit vectors that are directed along the positive x, y and positive z directions. Okay. So having said that, now let us see how can we go for the Cartesian vector representation. So since the three components of vector f act in the positive I, j and k directions, look here. So referring this sketch, we know that vector f, it has three components. Vector fx, that is acting in the positive x direction because the arrow is directed from the origin in the positive x direction. Similarly, fy is in the positive y direction, fz is also in the positive direction. Or in other words, the components marked in this sketch, vector fx, fy and fz are directed in the positive x axis, positive y axis and positive z axis. Okay. So accordingly, we can write down vector f as we discussed earlier. Vector f can be written as vector fx plus vector fy plus vector fz. Now, this is a very important statement. So how do we write a vector? Any vector, for example, the vectorial component in the x direction is equal to the magnitude of this vectorial component, which is written as vector fx, which is written as simply fx. So remember here fx means, let me go back to this sketch. Fx means it is the length of this vector, or it is nothing but the magnitude of this vector. Okay, so fx is the magnitude of the vectorial component vector fx. Okay, so vector fx can be written as its magnitude, that is fx, into the unit vector along its direction. We know that vector fx is directed along the positive x-axis. So this means that I is the unit vector along fx. So vector fx can be written as fx into I. Extending the similar argument, vector fy can be written as fy, that is nothing but the magnitude of the component, into j, and vector fz can be written as magnitude of the vectorial component, that is fz, into the unit vector along the z-axis. So please remember that any vector can be represented as its magnitude multiplied by the unit vector in that direction. Okay. So that is what is being written here. That is, each vector component is expressed in terms of its magnitude and the unit vector along its direction. So very clearly tells us one thing, that is, if we want to express a vector, we require two things. One, its magnitude. In addition to this, we also require a unit vector along its direction. So the magnitude and the direction completely defines a given vector. Okay. So now, how can we obtain the magnitude of a Cartesian vector in terms of the magnitude of its vectorial components? Okay, so this is what is written here. The magnitude of a Cartesian vector. Please remember, we say a vector is a Cartesian vector when it is expressed in terms of the Cartesian coordinate system, right? So the magnitude of a Cartesian vector can be expressed in terms of the magnitudes of its components. So look here. So what I want to do is, I want to express the length OA in terms of the length of these three components. Obviously we know that OA is the diagonal, okay, and Fx, Fy and Fz are the two adjacent sides of the prism. So accordingly, we know that the magnitude of the Cartesian vector, that is, remember the Cartesian vector was written as vector f. Its magnitude is written by f. So referring to this diagram, we can very easily say that vector OA square, that is f square, is nothing but fz square plus fx y square, right? So I am repeating, referring this triangle where we applied our parallelogram law once, or first, I can write my f square is equal to fz square plus fxy square. But I know that my fxy square is nothing but fx square plus fy square. So substituting this, what we obtain is, we can write down the magnitude of the Cartesian vector, that is f, as square root of fx square plus fy square plus fz square. So this is how it is derived. Simply f square can be written as f square xy plus f square z. That can be written as fx square plus fy square plus fz square. Or in other words, the magnitude of a Cartesian vector in this case designated by f is equal to square root of fx square plus fy square plus fz square. Remember, fx, fy and fz are the magnitude of its components. These are the magnitude of the components of the vector f. Okay. Now let me introduce you to another term, that is a coordinate direction angles. So we shall define the coordinate direction angles alpha, beta and gamma as the angle between the vector f and the positive x, y and z axis. So now let me take you to the other sketch. Look here, this is the same x, y, z system, okay, and my force vector f. it is represented by the diagonal of this parallelepiped, that is OA, right? And look here, my force vector F here, it makes angles with the x, y and z axis. Remember, OA is in space. As indicated in the sketch, let me just zoom it. Yes, you can say that this vector F, which is represented by OA, it makes an angle of alpha with the x-axis. It makes an angle of beta with the y-axis, and it also makes an angle gamma with the z-axis. So these angles alpha, beta and gamma, it defines the direction of vector F, and accordingly alpha, beta and gamma are what we call as the direction angles, because once we define alpha, beta and gamma, it means that the direction of the vector F is fully defined, and accordingly alpha, beta and gamma are what we call as the direction angles. Please remember that the minimum value of this direction angle is 0 and the maximum is 180 degrees. Okay, so alpha, beta and gamma, they vary from 0 and 180 degree. Now let us find out, once we know the components fx, fy and fz, how do we calculate the angles alpha, beta and gamma? Look here, let me just zoom this figure. Yes, here let us focus on the triangle OA small b. Okay, so we are considering the triangle OAB. Now look here, the angle OBA, it is 90 degrees. Though it is not possible to show it as a 90 degree properly in this sketch. Why this is 90 degree? Because we know that the line, okay, the line AB, okay, the line AB, it is on this rectangular face. Okay, it is on this rectangular surface or one face of this prism, and we know that this face of this prism on which the line AB lies, it is perpendicular to the x-axis. So if a surface is perpendicular to an axis, it means that any line on this surface should be normal to the concerned axis, right? Accordingly, we can say that the line AB, okay, it is lying on the front face of this prism. Accordingly, BB should be normal to my x-axis. So it does mean that my angle OBA, it is equal to 90 degrees. Accordingly, you can write down cos alpha. What will be cos alpha? Cos alpha is nothing but my adjacent side. Adjacent side is nothing but my fx divided by the hypotenuse. What is the hypotenuse? That is the side opposite to 90 degrees. That is my f. Okay. So this is what is written here. So referring this diagram, we can write down the cos alpha is equal to OB by OA. So you can have OB by OA is my cos alpha. What is OB? OB is fx. Look here, this is my OB. It is nothing but, it is the magnitude of this length. OB is nothing but the magnitude of the component vector fx. So OB is fx and OA, it is nothing but it is the magnitude of the vector f, which is identified by symbol letter f. So my cos alpha is fx by f. What does it mean? It means that the magnitude of the x component fx is equal to f into cos alpha. Now similarly, if we consider the other triangles, we can write down my cos beta as fy by f and cos gamma is equal to fz by f. What does it mean? It does mean that if we know the magnitude of the components of the vector along the x, y and z axis, that means if I know the value of fx, fy and fz, knowing the magnitude of the vector f, you can easily calculate the direction angles alpha, beta and gamma using these relations. So these numbers are known as, that is, please remember, alpha, beta and gamma, they are known as the direction angles because they are angles, and the terms cos alpha, cos beta and cos gamma, They are known as direction cosines because everything is cos of some angle, cos of alpha. So it's a direction cosine with respect to x-axis. Cos of beta, it's a direction cosine with respect to y-axis. And cos gamma is the direction cosine of vector f with respect to the z-axis. So while alpha, beta and gamma are known as the direction angles, cos alpha, cos beta and cos gamma, they are known as the direction cosines of vector f. Now let us calculate what about this cos square alpha plus cos square beta plus cos square gamma. We know what is cos alpha. Cos alpha is nothing but fx by f. So we have fx by f square plus what is cos beta? It is fy by f square plus what is cos gamma? It is fz by f square. Also we know that f square is nothing but fx square plus fy square plus fz square. What does it mean? It does mean that simplifying the right hand side, we simply obtain cos square alpha plus cos square beta plus cos square gamma is equal to 1. This is an important relationship that exists between the direction cosines, cos alpha, cos beta and cos gamma. So remember the direction cosines, I am repeating, direction cosines are related to the simple equation cos square alpha plus cos square beta plus cos square gamma is equal to 1. Now let us go for the next important topic, that is the definition of the unit vector along any direction. Because you know that if you want to define a vector in any direction, first and foremost important thing is that you need to calculate the unit vector along that direction. So how do we calculate the unit vector along a given direction? So now referring the same sketch, we can write down the unit vector along OA. So this is your OA. How do we express the unit vector along OA? So by the basic definition, we can write down the unit vector along OA. It is nothing but it is vector UOA, right, is equal to vector OA divided by its magnitude. Okay, and that is equal to, we know that vector OA can be expressed in terms of the magnitude of its components as vector OA is nothing but fxi plus fyj plus fzk. This is the full definition of vector OA. This vectorial representation, this has to be divided by the magnitude of vector OA, which is nothing but f. Now we know that this can be written as fx by fi plus fy by fj plus fz by fk. And we also know that fx by f is nothing but cos alpha and fy by f is nothing but cos beta and fz by f is cos gamma. It does mean that the unit vector along a given direction can be expressed directly in terms of the associated direction cosines. This is what is written here. That is, the unit vector along any given direction UOA is equal to cos alpha I plus cos beta j plus cos gamma k. Which means that if we want to calculate the unit vector along any given direction, we require only the direction cosines alpha, beta and gamma. Now looking into this expression, we know that for this unit vector the components are cos alpha, components are cos beta and cos gamma. So if we know, so cos alpha is the x component of the unit vector, cos beta is the y component of the unit vector along the y-axis, and cos gamma is the component of the unit vector in the z direction. So also we know that cos square alpha plus cos square beta plus cos square gamma is equal to 1. What does it mean? It does mean that cos square alpha plus cos square beta plus cos square gamma is nothing but the square of the magnitude of the unit vector. That is nothing but the square root of 1. So this also checks our earlier relation between the unit vectors, between the supported direction angles cos square alpha plus cos square beta plus cos square gamma is equal to 1. Okay. So what does it mean? It does mean that the vector f which is identified through vector OA in this sketch, it is nothing but its magnitude, which is represented like this: magnitude of vector F into the unit vector along OA. So that is equal to its magnitude F into the unit vector along the direction is cos alpha I plus cos beta j plus cos gamma k. Right? So please remember, here f cos alpha is nothing but fx, and f cos beta is nothing but it is fy, and f cos gamma is nothing but it's fz. So it means that if we want to find out the unit vector, we require one, the direction cosines, cos alpha, cos beta, and cos gamma. Once we know the direction cosines, the corresponding unit vector in that direction can be written as cos alpha I plus cos beta j plus cos gamma k. And any vector f can be written as its magnitude multiplied by the unit vector in the direction of f. That is, magnitude of vector f we are denoting by symbol by the letter f into the unit vector is nothing but cos alpha I plus cos beta j plus cos gamma k. So please remember that whatever discussions we had our discussions in the 3 dimensions, where our vector OA is in the space. In many of the simple applications, we will have the 2-dimensional problems wherein we need to consider only 2 axes. For example, if a vector F is in the xy plane, as indicated here, look here. In this case, my vector F, it is in the xy plane, right? And which means that my gamma angle, what is my gamma angle? Gamma angle is my 90 degrees, right? Alpha is the angle which my vector F makes with x-axis. Beta is the angle which it makes with y-axis. And we know that my xy plane is perpendicular to z-axis, which means that the vector F should make an angle gamma equal to 90 degree, right? And also we know that when the vector F is in the xy plane, it is understood that its component in the z direction, that is fz, should be 0. So this means that vector f can be written as vector fx plus vector fy, because we know that my vector fz, vectorial component in the z direction, should be 0. Now, expressing in the Cartesian components, vector f can be written as fxi plus fyj. So remember, fx and fy are the magnitudes of the components of f in the x and y direction, right? And also we know that f should be is equal to square root of fx square plus fy square plus fz square. But here fz is 0. Means for a 2-dimensional problem we have f equal to square root of fx square plus fy square. Now referring the sketch, remember one very important thing: the angle between x and y is 90 degrees. Okay. So for the 3-dimensional purpose, I cannot draw it exactly 90 degree. Okay. It is drawn something like an isometric view. So the angle between x and y is 90 degree. What does it mean? It means that the corresponding components here are what we call as the orthogonal components, or we can also call it as the rectangular components. So fx and fy are the rectangular components of vector f. Okay. Further, referring to this sketch, we can say that the magnitude of my fx, that is the magnitude of this line, the magnitude of this vector, is nothing but f, that is nothing but the magnitude of vector f into cos alpha. So fx is f cos alpha, and what is fy? That's the magnitude of the component in the y direction. It is nothing but f into cos beta, which can be written as f into cos of 90 minus alpha, that is equal to f sin alpha. And further, we know that cos square alpha plus cos square beta plus cos square gamma is equal to 1. In this case, gamma is equal to 90 degrees, for which cos gamma is equal to 0. Or in other case, for a 2-dimensional problem as shown here, okay, we have cos square alpha plus cos square beta is equal to 1. Further, the unit vector along f is given by, obviously we know that it can be directly expressed in terms of direction cosines. Okay, that is cos alpha I plus cos beta j. Therefore, vector f here can be written as its magnitude multiplied by unit vector in its direction. And the magnitude of vector f is f, which is the length of this vector, okay, multiplied by cos alpha I plus cos beta j. So that is all for this entire class. So we'll come up with a new topic in the next class.